Energy. It's a word we use all the time, but what is it? In physics, it's the master concept. The most important rule, the law of conservation of energy, says you can't make new energy and you can't destroy it. This is a big deal. It means all the energy that will ever exist is already here. Our job and the goal of this standard is to learn how to track it. We're going to build a model, basically an equation, to calculate exactly where all the energy goes. So, what is energy? The textbook definition is the ability to do work. That's a bit circular. A better way to think about it is as a change maker. If you want to make something move, heat it up, or change it in any way, you need energy, because there are so many types of energy: motion, heat, light, chemical. It's like a universal currency. To keep track of it, we need a unit. In physics, that unit is the Joule, J. It's not a lot of energy. Lifting a small apple about 3 feet off the ground takes about 1 joule of energy. This next idea is the most important first step, and it's where most students make mistakes. Before we can track energy, we have to define our system. A system is just a box, a conceptual box. We draw a circle around the things we want to study. Is our system just the baseball, or is it the baseball and the bat, or the baseball, the bat, and the earth? The answer will change how we solve the problem. Everything outside the circle we've drawn is called the surroundings. Once we have our system, we need to know if it's isolated or not. An isolated system is a perfect bubble. No energy gets in, no energy gets out. Think of a perfect sealed thermos that never cools down. In reality, these don't exist, but we use them in physics problems to simplify things. The real world is full of non-isolated systems. You pour hot coffee into a mug. The coffee is your system. It's non-isolated because heat energy is leaving the system and flowing into the cooler air and the mug, the surroundings. Let's meet the most obvious form of energy, kinetic energy, or K dollars. This is the energy of motion. A moving car, a thrown baseball, a running person, they all have kinetic energy. The computational model for it is a formula, Ke nafrak 1 2 on mv $2. M-ton is the object's mass in kilograms, and $V is its velocity in meters per second. This formula lets us calculate a hard number in joules for the energy of any moving object. Let's look closer at that formula. Ke arn frac 1 2 tos mv $2. Notice the V is squared. This is incredibly important. Let's compare two cars. If a massive truck, double the mass, and a small car are going the same speed, the truck has double the K does. But if you take one car and double its speed, say from 30 to 60 mph, you don't just double the Ke, you quadruple it, because V gets squared, 2 errors $4. This is why speeding is so catastrophic. The energy in a crash and the damage it causes grows exponentially with speed. The second main form of energy is the opposite of K dollars. Potential energy, or P dollars, is stored energy. It's energy that's just waiting to be released. It's stored in the position or shape of an object. A boulder at the top of a cliff has potential energy. A stretched rubber band has potential energy. A compressed spring has potential energy. In all these cases, the energy is stored, ready to be converted into kinetic energy. The most common type we'll deal with is gravitational potential energy, PE dollar. This is the energy an object has just by being high up. The formula for it is PEG tau, mge taller. M tau is mass, g tau is the strength of gravity. On Earth, it's a constant, 9.8 mums $2, and h is the height. A 1 kilos book on a 2-meter high shelf has twice as much PE dollars as a 1 kilos book on a 1-meter high shelf. You did work to lift it, and that energy is now stored, waiting. The other common type is elastic potential energy, PE dollars. This is the energy stored in something stretchy or springy. Think of a slingshot or an archer's bow. When you pull it back, you're loading it with PE dollars. The formula PEE is She frac 1 2 kx $2 looks similar to the key one. K is just a number for how stiff the spring is. and xt is the distance you've stretched or compressed it. Just like with velocity, that $2 means if you pull a slingshot back twice as far, you're storing 4 times the energy. So what happens when we put these together? The sum of an object's kinetic and potential energy is called its mechanical energy, or me-dollars. Me cas ke plus po. Think of a skateboarder in a half pipe. At the very top edge, they stop for a split second. They have 0 k'd, but maximum p. Then they drop in. As they lose height, lose p, they gain speed, gain k. Their m is just the total of these two at any given moment. This brings us to the big one, the law of conservation of energy. This is the bedrock of all physics. It states that energy cannot be created out of thin air and it cannot be destroyed. It can only be transformed, like $P turning into $K, or transferred, like heat leaving a hot cup of coffee. The total amount of energy in the universe is fixed. Our job is to be energy accountants, tracking all the transactions. Let's go back to our isolated system, that perfect thermos. If no energy can get in or out, then the total energy inside that system must be constant. It must. So, for our skateboarder, if we pretend there's no friction or air resistance, an isolated system, his total me never changes. The energy just sloshes back and forth, P to key to P. But the sum, Ke plus P, is always the same number. This gives us our simplest model, me, initial, me, final, The classic example is a roller coaster. Let's assume it's an isolated system with no friction. At the top of the first giant hill, the cart is barely moving. It has maximum $G because its height is max and almost 0 KE. Then it falls. As it loses height, P dollars transforms into K dollars, and the cart's speed increases. At the very bottom, $0, so PE $0. All of that initial potential energy has been converted into K dollars. The cart is now at its maximum speed. This is the computational part of the standard. We can calculate this. Imagine a 100 kilo cart at the top of a 20-meter hill. Its initial PE dollars is mg torus, or 109.820, which is 19,600 joules. Since it's at rest, its kDs is 0. The total me dollars of the system is 19,600 joules. Now let it roll to the bottom. In our isolated system, the total me do must still be 19,600 joules. But since it's at $0, its P dollars is now 0. This means all 19,600 joules must have been converted to K dollars. So we know the cart has 19,600 joules of K dollars at the bottom. What good is that? Well, now we can solve for its speed. We know Ke sandwich frac Tawan 2 mv $2. So $9,600 sandwich to frac Tawana 2's 100 v $2. $9,600 is 50 v $2. Divide by 50 and you get V2 shared $392. Take the square root and V2 19.88 miats. We just built a computational model to predict the speed of a roller coaster, all based on its starting height. That's physics. But wait, we all know that's not quite right. A real roller coaster's speed would be a little less. Why? Because our isolated system assumption was wrong. The real world is non-isolated. Energy can leave the system. How? By doing work. Work is the physics term for an energy transfer caused by a force. When you push a box, you are doing work and adding energy to the box. Work can be positive or negative. When you push a box, you do positive work and add energy to it. But what about friction? Friction is a force that opposes motion. As the box slides, friction does negative work on the box, removing energy from it. This lost energy doesn't just poof, vanish. That would violate the law. It gets transformed into thermal energy or heat. If you rub your hands together, they get warm. You're using K dollars to do work against friction, and the result is E thermal. So, let's look at our roller coaster again, but this time in the real world. As the cart rolls, friction in the wheels and air resistance, which is just friction with the air, are constantly doing negative work. This work leaks me dollars out of the cart earth system. Where does it go? It goes into heating up the track, heating up the wheels, and heating up the air. The me dollars at the end is less than the me dollars at the beginning because a chunk of it was lost, transformed into heat. This gives us our final complete computational model. This is the one that always works. It's an energy budget. The initial energy of our system, KEI plus PEEK, plus any energy we add in, W cherry in aln, must equal the final energy, KEF plus PF, plus any energy that was lost or transferred out, E, loss, usually as heat from friction. This equation is the heart of HS-PS3-1. It's a spreadsheet for tracking all the energy. In the end, HS-PS3-1 just wants you to be an energy accountant. Energy is a quantity, a number in joules that we can track. Think of it like money. Your E initial is your starting bank balance. W in dollars is your paycheck. E final dollars is your new balance. E lost dollars is the money you paid in taxes or transaction fees. The numbers all have to add up. You can't have miscellaneous or unknown. Every single joule must be accounted for. That is the law of conservation of energy.